Okay. So sebenarnya kan kelas korang sangat senyap tau compared to other classes. So saya tak tahu korang malu dengan saya ke. Saya tak tahu. So I hope everyone is going to be comfortable over time. Okay, so harapnya akan lebih bising sikit lah. Saya rasa awkward bila korang senyap. Okay, so let's do our recap. So we talked about Newton's law, which is number 1, number 2, and number 3. So Newton's law says that the first one was about law of inertia. So it is the natural tendency of an object to continue its state of motion either at rest ataupun at a constant velocity, and that is inertia lah. So that is the law of inertia. So law of inertia, the way to quantify law of inertia is to use momentum, and momentum is affected by mass and velocity. So the higher your velocity, the higher your momentum, and the bigger your mass, the higher your momentum. So a bigger mass akan ada a greater inertia, and a higher velocity will have a greater inertia. Maksudnya lagi susah lah nak tukar dia punya direction, nak stop dia. So the inertia is greater. And how do you know if it's greater or not? It is dependent on mass and also velocity, ataupun it can be quantified by momentum. So that was Newton's first law. And then the second law states that F equals to ma if your mass is constant. If it is not constant, therefore you would have another component to this equation, which is dm dt, which means that your mass is changing over time times with velocity. What is acceleration in this case? Acceleration is dv dt, or the change in velocity over time. So it means the same thing. So this is Newton's second law. So they said that because we have this second law, you can actually rewrite the first law to say that the object has a natural tendency to stay at rest or move at a constant velocity unless acted on by a force. So law of inertia ni ada tambahan because of F equals to ma. So unless it is acted on by a force, then dia akan maintain. Kalau ada force yang act on it, then dia tak maintain its constant velocity ataupun at rest. And then we talk about the Newton's third law, which is equal and opposite forces. Okay, so a force cannot exist as an isolated force, as an isolated system. It has to have its pair lah. So the case that we saw was a box on a table, and the table applied force on the box due to gravitational force, and the table does not like this, so dia akan apply an exact amount of force back on the box, but it is opposite in direction. It is equal but opposite. So this is Newton's third law, equal and opposite. So that was Newton's third law. Where is my slide? Saya nak duplicate. No, saya nak buat new slide. And then we talked about the different types of forces. We had, if I have a box on a table, I don't know why I like this example. So we have this box on the table. I would have, to draw my free body diagram, I need to go at the center of the mass of my object, right? So the center of the mass for this box is obviously at the center lah sebab dia symmetrical. So kita boleh cakap lah, okay, kat sini is our center of mass. Kalau objek yang non-symmetrical is going to be a little bit harder. Tapi selalunya kita akan go for symmetrical objects because that is your syllabus lah basically. So always at the center of the object, and then you start writing your forces. So the first one, what do we have for a box on a table? What forces do we have here? Assume that it is at rest. What forces do we have? Anyone remembers?
Weight.
It has weight. Normal. Okay, great. So kita ada normal force. Normal force can be labeled as capital N or R. What does R mean? R is reaction force. So anytime you see reaction or you see normal, it means the same thing lah. Both are the same thing. And then we have weight. Great. So kita do weight. So W equals to mg, or you can say it is equal to Fg, or you can just label it as mg. It is understood that it is gravitational force. And then if this guy is at rest but ada string yang menarik dia this way, so there is a pulling, bukan pulling lah, the tension lah, tension force acting this way. This is a string and this is, siapa nama yang saya nak guna hari ni? Let me use Faris punya nama lah. Saya rasa Faris dah pernah kena kot. Tak apalah, sorry Faris. So this is Faris trying to tug on the box using a string. So akan ada pulling force, right? Pulling force on the box. So how would we label this tension force? How would we label this tension force? Is this already completed? Can I just label it T like this? Boleh tak? Yes or no? Everyone forgot already. Okay. So forces kena start daripada mana? Center of mass. So this is not correct. You write it on the box, it's not right. So this is wrong. This is just the figure lah, macam gambar in general. Tapi kalau kita cakap pasal free body diagram, we cannot accept this kind of diagram because free body diagram semua forces kena at the center of the mass. So the right way to draw this is, kita tahu ada string kat sini kan. So we draw the tension like this. So this is tension force. It is in the same direction as the string, but it must originate from the center of the mass. Tak boleh kat ujung-ujung, okay? Kena kat center. Okay, so if ada tension, so this guy obviously has the tendency to move walaupun dia at rest. So the tendency to move is to the right ataupun upwards. Tendency of motion lah kita cakap. Dia tak gerak lagi, tapi ada tendency tu, kalau tarik lebih sikit dia akan bergerak. So that is the tendency of motion. So if it is going to the right, what other forces will happen here? It has the tendency, but it is at rest. What forces do I have? Other than tension, akan ada apa tadi? Friction, yes. Which way would friction be?
Ke belakang.
The other way.
It has to always oppose the motion. So if we assume our motion is to the right, therefore this is the direction of your friction. And kita dah belajar friction punya equation, it is equal to mu r. What is mu? What is mu? Ingat lagi tak?
Coefficient.
Yes, it's a coefficient of friction. So, sekejap, dia tengah saving pula dah. Faster. Okay, so mu is coefficient of friction. Another class asked me, doktor macam mana nak eja mu? So dia Google, saya tak Google, dia Google untuk saya, ejaan dia macam ni, it's just mu. So that is your mu. Mu sebutan dia macam mu. Mu not, tak tahu, tak ada mu not, just mu So it's mu, okay. So this is the coefficient of friction. You have two types of coefficient of friction, which is static and kinetic. So if this guy is not moving, but it has the tendency to move, which coefficient should I use? Static or kinetic? Static or kinetic?
Static.
Static because it has a tendency to move but it's not moving. So kenapa pilih static?
Static.
Because you're at rest.
Because it is still at rest, correct? So when it's not moving, it is at rest. So static means not moving. Static ni mean pegun pegun. So you use the coefficient of friction yang static. So this would be mu s. If the problem does not give you mu s or mu k, dia bagi mu sahaja, just use it as it is. You don't have to care about the static or kinetic. Okay, so typically static coefficient has a greater value than kinetic. It is harder to move an object that is at rest compared to when it is moving. So static punya coefficient selalunya lagi tinggi lah daripada kinetic kebiasaannya. But hopefully kita tak jumpalah keadaan yang kinetic lagi tinggi. But okay, so F equals to F friction, force of friction equals to mu R. R is your reaction force or your normal. Okay, so if you wanted to solve for friction, you would have to know what is your R. Okay, so kalau kita punya box ni punya string, kan kita ada box and then we have our string, and let's say Faris dah tak tarik, tapi Faris gantung dekat dinding. Gantung dekat dinding So how would that look like? Macam ni. Adalah cangkuk dia. Okay, so Faris gantung dekat dinding, saya tak tahu kenapa, adalah sebab-sebab dia yang tertentu dia nak buat macam ni, kenapa. So the box is connected by a string to the wall is slanted. What is the tension acting on this string over here? How would I draw it? Macam mana nak lukis tension dekat wall ni? What is the condition for tension force? So if I have a rope, right? Two guys are pulling on this rope. So each will exert tension force. Where is the direction of tension? No one remembers? Okay, so the direction of tension force is towards the center of the rope. So if A is applying tarik dia punya tali tu, so the tension force is towards the center of the rope. This is called T. And this guy B is tarik juga rope. The tension on this rope is towards the center. Okay, so tension force is always towards the center of the rope or the string. So back to our question, Faris dia letak string ni sangkut dekat dinding. Where is direction of tension here? Dekat dinding ni. Kat mana arah dia?
To the box.
Towards the box or towards the center of the rope. Betul. So it's easy kena ingat macam tu je. Towards the center. You don't have to be confused about tension. It's always towards the center. Your string is like this. Where is direction tension? This way. Always towards the center. Tak kisah arah macam mana pun. Apa arah lagi let's say we have a pulley. Pulley dia macam ni. Pulley ni is smooth. Always towards the center. Kalau ada objek kat sini, ada objek kat sini. Tension force is like this. Tension force is like this. It is towards the center of the rope. Okay, towards the center. Mana center? Sini. Situlah. Okay. So that is your revision on the forces that we have learned last time. So kita akan sambung. Tak apa lagi. Okay. So I need to cover one more thing. And then did we talk about a box on an inclined plane yet or not? Before kita dah belajar tak pasal ni?
No.
Belum Okay, so saya cerita lah. So if we have a box on an inclined plane, this is your box, this is an inclined plane, and this inclined plane has an angle of theta. Okay, has an angle of theta. So if I wanted to draw my free body diagram for this box, I would have to start from the center of the box, and my force of gravity is downwards, walaupun slanted. So this is mg. And this box has the tendency to slide off the incline, sebab kalau kita duduk atas gelongsor pun, kita rasa nak terjatuh kan. So benda yang atas the slanted surface akan ada that tendency of motion to downwards. So this is the tendency of motion. Kita tak tahu lagi dia bergerak ataupun at rest ke, tapi kita tahulah akan ada tendency of motion tu. So assuming that this box is at rest, I would have friction, sebab dia ada tendency of motion to the right, I would still have friction that is holding the box on the incline. Okay, kalau tak ada friction, dia akan menggelongsor lah. So the friction is holding the box static. Okay, kalau permukaan gelongsor ni tak kasar, then box tu akan menggelongsor. So we need friction to keep the box on the slide or the inclined plane. And then we have, what else do we have? We have reaction force that is perpendicular to the surface. What does perpendicular to the surface mean? It means that it is always 90 degrees with respect to the surface that it is on. R ni special, it is always perpendicular to the surface. Friction pula parallel dan opposite to motion. Okay, so that is your friction, reaction, and it has the tendency of motion to the right. So now that we have this box on an inclined plane, the situation changes a bit. So I want you guys to focus here. Bila kita ada box on an inclined plane, our friction is parallel to the motion, our reaction force is perpendicular to the surface, and our mg is not in the same axis as R, it's not in the same axis as F. So if I wanted to declare my axis, I would say this is my x-axis and this is my y-axis. This is my new x-axis and this is my new y-axis. You can also call this as parallel axis. Oops. Sorry. You can also call this as parallel axis. Ni simbol parallel and you can also call this perpendicular axis. Boleh. But I prefer to call it x and y sebab senang nak ingat. So this is my new x-axis and this is my new y-axis. Dia dah sengit. So my mg is not in my x-axis and is not in my y-axis. First of all, kenapa saya nak buat new x-axis? Kenapa tak pakai yang lama je? Sebab it is easier to solve equations when everything is on the x-axis and on the y-axis. So sekarang ni kita ada dua forces in x and in the y. So it's better for me to choose this axis sebab forces semua dalam axis tu. So kalau saya nak maintain juga boleh. Saya nak maintain juga x-axis yang lama. Kita buang dulu ni. Bear with me dulu with this explanation. It's quite long. So if I wanted to maintain the original x-axis which is over here and over here. This is y and this is x. Kan? Macam tu. So now my R and my F is not on this original x-axis. Maksudnya saya kena resolve. So that takes work. And saya hanya ada mg sahaja dalam original x-axis and y-axis. So to make things simpler, I just go for my new axis and I declare everything to be on the new y-axis. So how does that work? Let's do that. So this is my new x-axis and this is my new y-axis. Sabar dulu sekejap Okay, so now I have my y-axis ada R and my x-axis ada F. So ada dua forces compared to just now, satu je force dalam my y-axis, right? So I prefer this setup lah sebab my forces are within this axis. Only my mg is not. So how do I make my mg or my weight to be in this y and x axis? Senang je, I just need to resolve it. So let's resolve my mg. How do I resolve it? We have this angle of the inclined plane. When I have this angle, it means that the angle over here is also theta. Okay, when I have an angle for the inclined plane like this, theta, then my mg and my new y-axis punya angle between them is theta. Okay, so now I can resolve my weight to become mg cosine theta, and which is this way, and my mg sine theta over here. So now I resolve my mg into the new y-axis and into the new x-axis. So now everything is on the axis and it will be easy for me to add them on later on. Now, what did I want to see? Okay, so what if my inclined plane is this way? So my theta is here and my box is on this incline, okay? And my mg is this way. My tendency of motion is this way. So it shouldn't be part of the free body diagram. So saya label kat luar free body diagram. It shouldn't be part of it because it's not a force. So this would have friction over here, terbalik to the motion. Reaction is perpendicular to the surface and I want everything on X and Y axis. So X axis over here, Y axis over here. So I need to resolve my mg. My angle theta would be in between the Y axis and the mg. So theta is here. Theta yang sama dengan incline. Jangan ada theta lain, theta yang sama. So theta is going to be between mg and also the new y-axis. So this becomes mg cosine theta. Remember I told you the axis that touches the theta will get the cosine and the axis that does not touch the angle will get the sine. So this guy would be, this is your mg cosine theta and this is your mg sine theta. Okay, wow. So we resolve the mg to be on the new x-axis. So now if I wanted to add what are the forces in the x-axis, I can say, oh, it's mg sine theta minus friction. So friction terbalik. And then if I wanted to ask, okay, what is the forces in the y-axis? It is reaction force minus mg cosine theta. So here we are assuming down here is positive, up here is positive. Apa-apa yang ke bawah dan ke kanan adalah negatif. Boleh tukar. Let's say you don't want mg sin theta to be positive, you can change it. You want friction to be positive, boleh. You can put that into your equation. Okay, so I hope everyone is clear on resolving mg. Nanti kita akan tengok examples and we will use this again. And memang selalu ada incline plane. So I hope everyone can try to understand. If you are still blur about this, please try to understand it. Okay, what else did I want to talk about? Okay. Okay, tadi kan kita cakap pasal incline plane and the mg resolve into mg sin theta and mg cosine theta. So when your mg sin theta is less than friction, okay, let's call this as force going down. Mg sin theta is the force that is pulling the box to going downwards, right? So we call this as F down, buat masa ni. So we call this as F down. If F down is less than friction, then your box will stay static. Right? So if the F down is less than friction, the box will stay static sebab friction tahan dia daripada bergerak. But what if the F down is equal to friction? Then this is called limit of static friction. Limit of static friction. At this point, your friction punya coefficient is still using mu s at this point. Tapi dia dah sampai limit dia sebab F down ni bila dia dah equal to friction, dia dah almost nak gerak tapi belum gerak lagi. So dia masih static. So we are still using mu s. But at this point, we say that, okay, the friction is at the limit of static friction. So when F down is greater than friction, maksudnya force tu lagi kuat daripada friction, maksudnya dia akan menggelongso. So now the friction no longer is using the static coefficient sebab sekarang dia bergerak. So we use the kinetic friction. At this point, dia akan pakai kinetic friction sebab dia dah start bergerak. When F down is greater than friction, the pulling force is greater than friction. Maksudnya friction tak boleh dah tahan box tu sebab pulling force lagi besar. Then it starts to move. Therefore, your friction punya value will use the coefficient of kinetic friction. Okay. So ada dua situasi, F down less than friction, box static. Box tak gerak sebab friction tahan. F down equals to friction. Box masih static tapi dah sampai limit dia. Kalau lebih dari limit ni dia akan gerak tapi dia belum gerak lagi. So masih box static. So masih pakai mu s. So this is called the limit of static friction. When F down is greater than friction, box is moving. And now you have to use mu k, coefficient of kinetic friction. Alamak, this is like too ugly. I should have made a table. So this is kat bawah Box moves and this one is box masih static. This one is box static. So let me just make this. Okay. Sorry lah, table ni is terrible. Okay, so F down less than F, static. F down, ataupun kadang-kadang F down ni dia terlalu kurang daripada friction. No, tak ada. So when F down is less than friction, box is static, F down equals to F. This is the limit of static friction. F down greater than F, the box starts to move. Okay, so that is just about friction. Okay. Okay, we have not covered this one yet, I think. So when we have a direct pull or push, we don't actually label this as anything. It doesn't have any F ke, tak ada nama lah specific for direct push or pull force. But we can label it as FP or we can just label it with the magnitude terus. So in this case, this guy is pulling the box with 10 Newton. So I can just label it 10 Newton or I can label it as force pulling ataupun I can label it as pull, but preferably letak FP lah ataupun dia punya nombor. Okay, so that is for generic forces yang bukan tension, bukan friction, bukan gravitational force, bukan reaction force. It's push or pull. Kita akan label with magnitude ataupun FP or F1, FA boleh. So this is also a contact force. This is a push force. In this case, the force is applied 40 degrees with respect to the y-axis, with respect to the vertical axis. So if I wanted to know, hey, what's the force acting horizontally on this box? I need to resolve this F. So to resolve it, we use what we've learned in chapter 1. Resolve je lah kan. So this is, so the axis that is touching the angle gets the cosine. So this is F cosine 40 and this would be F sine 40. So the force applied horizontally on the box is equal to F sine 40. The force applied vertically on the box is F cosine 40 because this is what is applied pushing upwards and this is what is being applied pushing to the right. So this is how you resolve it, okay? And then we have, oh, kita dah go over this one. Okay. Okay, so this is another instance of tension force. This is someone trying to pull the spring and this is the mass that is connected to the spring. So dua-dua ni ada string Dua-dua ada string connected by a string. So when we have strings, we have tension force. And the tension force must act towards the center of the whole string. Walaupun ni bukan string, tapi dia still macam rope, right? Macam tali lah. So we still consider it to be part of the system. Therefore, the tension is always towards the center of the rope. Walaupun benda alam ni spring. Okay, and then we have this box. Saya dah cerita tadi, always towards the center of the spring, assuming this pulley is smooth. When your pulley is not smooth, then you would have other forces macam friction, ada apa lagi? Contact force, benda lah, ada macam-macam. So you will always assume that the pulley is smooth so that tak ada force yang lain-lain dalam ni. So kita akan cakap, okay, so the tension, kita ada tension force here, which is from the string. Kita anggap the pulley is smooth, therefore we only have tension forces acting on the string. Okay. Then this is another instance. This is a box connected by a rope, and this is a smooth pulley. Okay, and then this is a mass, and it is connected by the rope. So this is tension force, and this is also tension force. When the pulley is smooth, now this is another thing that I forgot to mention. When the pulley is smooth, your T is equal. So if this is T1, this is also T1. This is the case when the pulley is smooth. Your tension are equal on both sides. Walaupun mass dia berbeza, tension dia akan tetap sama sebab dia from the same system, which is the rope. But if I wanted to draw the free body diagram for this mass, kita buat this is mg, and this is tension 1, this is reaction force, and I assume that this guy, the surface is not smooth, so we have friction opposing the motion. So if this mass is heavier than mass 1, then the tendency of motion is this way, right? But if mass 1, M2 is greater than M1. But if M1 is lagi berat daripada M2, M1 is heavier than M2, then your motion would be towards the right. Sebab dia akan tarik. Motion if M1 is greater than M2. So ikut logik lah ni kan. Kalau lagi berat, dia akan tarik. Kalau M2 lagi berat, dia akan tarik. So now we go for M2 lagi berat pada M1 lah. Kita nak make things easier. So friction will oppose the tendency of motion. So this is where your friction is acting. Forgot to label it as just small f. So you have reaction force, friction, tension, mg. We're not done yet. We have to resolve mg into its components. So everything is on the x and y axis. So mg, this would be theta. This would be mg cosine theta. Okay. And this would be mg sine theta. Okay, so does anyone have any questions so far about this object punya free body diagram? Soalan tak? You can also type it in the box if you're too shy to say anything.
No.
No questions?
No.
Everyone's okay? All right. So kita ada
Okay.
two objects, right? We have two masses here, mass 1 and mass 2. This means that we would have two free body diagrams. So if this is my new axis, let me write it. This is my x and this is my y. This is specifically the axis for my mass number 1. It doesn't mean that my mass number 2 has to follow this axis. So this guy can still maintain x-axis like this and y-axis like this. Boleh. Your axis can be different for your different free body diagrams. So in this case, the T1 is in the y-axis. This is mg. This is mg. What other forces do we have here? Do we have reaction force for mass number 2? Do we have reaction force or not? Banyak ni.
No,
No, because
because it's not touching surface.
Yes, correct. So it's not touching any surface, tak ada meja, tak ada apa kat situ. So there's no reaction force. There's only tension force and it comes from the string. Kalau ada string memang ada tension force. Kalau tak ada string, tak ada tension force. So always when you have the string, you will have tension force. Okay, so the free body diagram for this guy, kena connect lah all the forces together. So this is tension and this is mg or weight. Do I have to resolve this? No, because it's already in the x and y axis. Okay, so let's look at this second diagram pula. This looks a little bit harder. So in this case, we have a rope and we have a mass. So if I wanted to draw the free body diagram for this mass, I start from the center and you would have mg, which is weight, and you would have tension, which is from the rope. So it would go in the same direction. So this would be tension B from force P, and this would be tension A. Okay, and I won't have any reaction because it is suspended in air. It's not touching any surface except for the string. So I would only have tension on the top. Okay, so that is the free body diagram for this mass. But what is the tension force over at the wall? How would I draw the tension force there? What is the condition for tension force? To draw
Towards the center.
towards the center of the string or the rope. So this is the center. This is your T. And T at this point is equal to, if this is TA, this is also TA. And if this guy is TB, this is also TB. Because why? Because it is from the same rope. TA and this is TB. Saya letak je dalam free body diagram ni, sebenarnya dia dekat sini. But free body diagram kena pada center of mass, so I arranged it into this center. Sebenarnya it's here. Okay, so that is your TB. It will be equal. TA is not equal to TB, but TB will be equal to TB. TA will be equal to TA. They are from the same string. This guy is from the same string. It is equal. They are acting towards the same center. They are equal. Okay. So that is your what nama dia? An object suspended by a string. So let's talk about your experiment from yesterday. So layout sekejap sexual design layout blank. Okay, let me make this bigger. So let's talk about the one that we did yesterday. You guys did it. So assuming this is your table and the tempat base dia, which is not important, and then you had to place some heavy object as your pulley and you had to connect it to strings, your objects to strings, right? So assuming that this is your object and dia akan suspended macam ni lah. So this is your object number 1, object number 2, and object number 3. So they are suspended. So your object would have mg on each object. They will have their own mg. If this is mass 1, I need to label this as m1, m2, and m3. What else do I have over here? This is
Tension.
we have tension, right? So tension will be acting this way. This is tension 1 and this is tension 2. Ayo, kenapa string saya kat ujung? This is tension 2. Okay. And this is tension 3. Oops. This is tension 3. Where is the tension at this pulley?
Center of the
Where's the center of the rope?
center.
So it will be equal. Let's use red. So this is, oh tak nampak. Let's use the orange balik. So this would be T1, this would be T2, and this would be T3. Now we haven't talked about this, but this system is in equilibrium. Kita cakap sikit je hari tu. Equilibrium. This system is in equilibrium because it's not moving, it's static. System, sorry, system is in equilibrium. Okay, saya curi gambar taibah semalam, saya forward kat korang. Did I forward it? Yes. So system is in equilibrium. What does that mean? It means that the F net is equal to 0. And when your F net is equal to 0, your net in the Y should be equal to 0. Your net in the X should be also equal to 0. Walaupun ada MG, walaupun ada T, it is still equal to 0. Maksudnya they will cancel out with each other in a way that diorang cancel out, so tak ada force yang tinggal, dia akan jadi kosong. That is why it is static, so it's not moving. So when you have F equals to 0, this means that 0 equals to MA. Mass cannot be 0 because it's mass. So the only thing that can be 0 here is your A. When your A is 0, it's either you have constant velocity or it's not moving at all, it's at rest. So in this case, your A is equal to 0 and it is at rest. Therefore, the system is in equilibrium, not moving. Okay, so this was what we did yesterday. So when they tell you the system is in equilibrium, you start with F equals to 0. And in this case, you have 3 forces. Kita akan cakap, kita akan resolve it into X and Y lah. I think you guys know how to do that. So T1x plus T2x plus T3x will be equal to 0. And then Fy, net in the Fy, T1y, T2y plus T3y. Cuma nak tahu y dengan x dia, resolve pakai angle. Dalam manual tu dia bagi angle kan, resolve it. So this would be equal to 0. Okay. So that is an introduction dululah. Nanti kita akan go for the explanation. Kita dah cakap pasal free body diagram. Okay, dia suruh draw a free body diagram for all the cases below. Okay, can I get, I'm gonna ask you guys, we haven't done this one yet, right? Dah ke belum?
Belum.
Belum kan? Ni saya dah cerita tapi korang boleh buat sendiri kan? Okay, saya nak Hazira to do the first one. Okay, everyone else please try as well. And also Izzati Alia for the second one. Ini saya dah cerita dah, so hopefully boleh buat. Okay, so let's try for 5 minutes and we come back and discuss. Please try yourself, test your understanding. Kalau blur, make sure tak blur lepas ni. This is the free body diagram is your first step to everything, so make sure you understand it. Okay, 5 minutes from now, 2:55. Okay, please help your friend. If she can't answer it, you need to help. Okay, 1 more minute to go. Hazira dengan Izati dah settle ke buat? Senang je kan? Hazira dah siap tak?
Kejap dulu.
Okay. Izati Alia, siap tak?
Ya.
Apa dia? Dah siap dah? Hello?
Tengah.
Oh, tengah, okay. Okay, saya ada check kat sini. Doktor, saya nak tanya, friction tu kan walaupun friction berlaku dekat surface plane and object, kita kena tetap label dari center. Yes, betul. Kena label dari center walaupun dia berlaku dekat tepi ni. Dia berlaku kat sini kan? Tapi kita kena label kat sini juga. Sebab this is what free body diagram is. Dia akan kumpulkan semua forces dekat center of mass. That's really good question. Nanti saya cakap lagi sikit pasal ni. Okay, Hazira, are you done?
Yes.
Okay, tak apa yang salah. Kalau salah tak apa, kita belajar sama-sama. There's no harm in trying. Okay, Hazira, how did you do it?
First, the the R is towards upward
Okay, apa?
at the center of the box.
Okay, that is your R. Okay, what else?
Bawah dia gravitational force,
Okay, MG.
kiri frictional force, kiri center box.
Okay, friction.
Lepas tu towards the hand yang tarik tu ada tension.
Okay. Towards the hand yang tarik tu ada tension. Macam ni? Okay.
Lepas tu 30 degree dekat x-axis punya bawah.
Oh,
Punya.
good. Okay. So how would you resolve the T? Pakai angle. Lepas tu? What is your x-axis in this case? Ada tak? Tak apa, teka je. Salah tak apa.
Blur lah doktor.
Saya bagi hint. So your x-axis is this way. So how would you resolve your T in the x-axis? Macam nak resolve? What is the equation to resolve?
T cosine 30.
T cosine 30, thank you. And what about in the y-axis?
T sine 30.
T sine 30. So always try to resolve your vectors into the axis. Kena, sebab nanti kita akan guna dalam equation later on. Okay, so T cosine 30, T sine 30. Sebab x-axis touching 30 degrees, therefore the x-axis gets the cosine. This is Tx and this is Ty. In this case, your x-axis and y-axis, the normal one lah sebab dia tak slanted. Okay, what about the tension force dekat tangan ni? Ada tak Hazira? Ada tak?
Ada.
Okay, towards
the box.
towards the box, betul. So this is also equal to T. Kalau diorang tanya lah. Kalau tak tanya, selalunya tak tanya. Tapi kena tahulah. Tension always towards the center of the string. Okay. Okay, so I have a question from Rai. Sorry doktor nak tanya, kalau object on inclined plane tadi, angle for mg tu memang to touch the y axis ke? Okay, so kita ada incline and this is the box. This was our angle and our mg is this way. Sorry, our mg is this way and your angle theta is over here. Ada cara nak dapatkan this angle tapi saya tak ingat macam mana. Ada geometry. I think it's modern maths. But I don't remember how to get it. So saya memang memorize. Okay, so theta kena dekat sebelah y axis yang baru. Itu je cara saya ingat. But you guys can actually find it out using geometry. Kan triangle ada 180 degrees. Lepas tu pakailah benda-benda angle tu lah. You will get it. You will get that theta over there. Okay, so that is how I remember it. I just memorize. So that's not good sebenarnya kena tahulah macam mana nak tahu dapat theta. It's not good for me sebenarnya. Okay, so theta is between the y-axis and also mg. Yes. Okay, back to this one. I think we are done. So we have in the x-axis we have friction to the left and we have tx to the right. And in the y-axis, we have r going upwards, we have t sine 30 going upwards, and we have mg going downwards. Okay, well done, everyone, and Hazira as well. So Izzati, how did you do the traffic light?
Yang tension tu dia pergi dekat center. Tension 1.
Okay, tension 1 goes to center. Oops. Okay,
Okay, tension tu pun sama.
towards the center of the string. Okay,
Lepas tu mg dekat bawah.
FG dekat sini ke?
Bukan, bawah lagi.
Bawah lagi, okay. So dekat sini.
Bawah.
So where does T3 go? Anyone wants to help? Izzati?
At the center, downwards.
Apa? Tension. At the center and downwards. Okay.
Yes.
So traffic light ni hanya ada mg je ke? Okay, tension dia ada pair kan selalu. So pair of T1 is here. The pair for T2 is here towards the center of the rope. T3 is going down. Where's the pair? Saya tunjuk saya kasih hint lagi. So this is T3. Where is the pair? Nampak tak?
Atas traffic light tu.
Kat atas traffic light, yes. But it will start from the center of the mass. Sebab kita ada dua sistem. Satu sistem tali, satu sistem, kita ada dua center of mass. Satu center dekat string ni, satu lagi center of mass dekat traffic light. So traffic light ni ada dua forces acting on it. One is mg and one is T3. And kat center of mass ni, center of string ni ada T2, T1 and also T3. Betul. Now, when this traffic light is in equilibrium, meaning to say it's not moving, I can see that, okay, F net is equal to 0. Therefore, Fy is equal to 0. Dalam case ni, kita tengok the first free body diagram. If net Fy equals to 0, therefore T3 plus mg, or in this case minus mg, so mg ke bawah, T3 minus mg will be equal to 0. Therefore, I can find out what is T3. T3 is equal to mg. This is if it is in equilibrium. Semua orang macam, apa ni? Okay, tak apa. Saya introduce dulu. Nanti kita akan cakap lagi pasal ni. So, free body diagram ni betul lah. Thank you everyone that helped, and also Izzati Alia. Thank you. So well done everyone. Okay, next one. Let's ask Kita buat terus lah, tak payahlah tunggu 5 minit. I think everyone dah ada idea sikit. Can I get my Shahira for the first one and Nur Aizat for the second one? Boleh tak? Okay, Mai. Let's do this. Kita dah pernah bincang dah dalam kelas. What is your free body diagram? How would you draw it?
Yang tension force tu yang kat tengah-tengah, yang dekat bulat tu.
Tension force tu tengah-tengah. Okay, kalau from object A, would it be to the right or to the left? Macam mana?
Right.
To the right, okay. To the right, so that is your tension number 1. What else for object A?
MG dia ke bawah.
MG ke bawah, betul?
R dia ke atas.
Dia ke atas. Okay.
Friction dia ke kiri.
Kanan kiri. So we are assuming that this guy is going to go down lah. Okay. Alright. So the object B. Good.
Tension dia ke atas.
Okay, betul. What else? All objects have? All objects have? Awak duduk dekat atas Earth ke, dekat Moon ke, akan ada
Gravity.
Gravity. So what do you have here?
Ke bawah.
Ke bawah, mg. Gravitational force. Okay, thank you. Good. Betul. Tak tahulah korang tengok buku ke apa, but betul. If you refer to the book and you understand how to do it, that's fine. Next one, Isaac. How do you draw your free body diagram?
Yang untuk M1 tu, ada tension dia ke atas.
Tension dia ke atas, okay.
Itu kita ada MG
Okay,
bawah.
MG. So this is M1G, correct?
Itu yang A2 tu kita ada MG juga ke bawah, M2G.
M2G, betul.
Dia ada tension ke atas juga.
Tension ke atas juga. Okay, so if I say that this pulley is smooth, would T1 be equal to T2 or is T1 not equal to T2?
Not equal.
Kalau pulley smooth.
Yeah. Equal? Equal.
Kalau pulley is smooth, then if they are connected by the same string, therefore T1 is equal to T2. Selalunya korang akan label this as the same tension lah, T and T. So T is equal to T. Same, maksudnya sama lah. The value would be the same kalau the pulley is smooth. Okay, well done. Thank you.
Thank you. Okay.
Ada soalan ke?
Yang pertama tu kan dia punya berat atas dia lagi besar, so friction dia pun dia ada.
Continue. Dia ada
maksudnya apa? Dia bergerak ke?
Boleh
ada
kalau
friction.
Ya, faham. Saya faham soalan awak. So sekarang ni siapa yang tanya tu Rai
Patricia.
Oh, Patricia. Sorry, Patricia. So soalan Patricia is mass yang pertama ni, mass for object A is 5 kg and mass for object B is 2 kg. So kita logically lah, kita akan tengok, okay, so box ni lagi berat daripada yang ni. So selalunya dia tak gerak lah. Ataupun kalau dia nak gerak pun, dia akan gerak ke kiri ke? Kalau dia nak gerak.
Tak.
Dia akan gerak ke kanan juga kan? Kalau dia nak gerak sekalipun, dia akan gerak ke kanan kan? So tendency of motion is still to the right. Walaupun dia lagi berat. But sometimes, walaupun dia lagi berat, kadang-kadang table ni is super smooth. So the friction, kadang-kadang ada instances where the friction is so small that the T1 is greater. So when T1 is greater than F, dia akan move to the right. When T1 is greater than F, force sebelah kanan lebih tinggi daripada force sebelah kiri, dia akan move to the right. Kalau F is greater than T1, maksudnya friction lagi besar daripada T1, dia akan static je. Dia tak akan gerak. Friction is not a force that moves object. Dia akan hanya oppose ataupun make it at rest. So if friction is greater than T1, dia akan static. There's no instance where friction is greater than T1, dia akan bergerak ke belakang. That is not how friction works. That would become a push force instead of friction sebab dia bergerak. So, tapi soalan tu betul. Dia lagi berat. So selalunya dia akan tak bergerak lah. Okay. But assuming that dia ada tendency to move to the right, therefore the friction untuk bagi dia stay still would be to the left. Okay. Faham tak? Macam Syah okey ke?
Faham.
Okay.
Thank you, Doktor.
Welcome. So, okay. So soalan yang Isaac jawab tadi tu, dia ada tulis acceleration tau. Which means that this system is not in equilibrium. Kalau equilibrium, kita cakap F net equals to 0. But in this case, we have acceleration 1 going upwards, acceleration 2 going downwards. Acceleration 1 refers to acceleration by mass 1 and acceleration 2 refers to acceleration by mass 2. Now, because they are from the same system, boleh ke kita punya mass ni sebelah kanan bergerak 10 meter per second squared? Contoh, acceleration dia is going down 10 meter per second squared, and then untuk A1 going up, A1 dia adalah 5 meter per second squared. Boleh tak jadi macam tu? Boleh tak dia berbeza-beza acceleration dia?
Tak boleh.
Tak boleh kan? Kalau kita tarik
Tak
sebelah
boleh.
sini dengan kelajuan let's say 2 meter per second squared, sebelah yang tertarik ni pun akan naik pada kadar kelajuan yang sama. So sebenarnya A1 akan equal to A2. Saja je lah ada trik korang kat sini. So A1 dengan A2. So jangan tertipu. So when it is from the same system, if it moves, it will have the same acceleration. So kita akan masuk ni kemudian lah. Tapi saya nak introduce lagi about kadang-kadang sistem kita in equilibrium. When it is in equilibrium, F net is equal to 0. When it is not in equilibrium, we have acceleration. Okay, so now we talk about net force. Kita masuk net force pula. Kita dah cerita sikit lah pasal net force before this. I told you about F net. Kita boleh label this as F net like this, or you can write it F subscript net, means the same thing. This means sum. Kan sum kan, math punya notation. Summation of forces ataupun F net, daya bersih. So F net is equal to F1 plus F2. But if your vectors are not in the same axis, you cannot add them together. So let's say F1 kat sini is F prop and F resist. They are on the same axis, and I say towards the right is positive and towards the left is negative. So I say, okay, F prop is positive, F resist is negative. Dia pergi ke kiri. F prop pergi ke kanan, positif lah. So F prop, let's say it's 10 Newton, F resist is 5 Newton. So, kita boleh tulis net in the Fx is equal to positive 10 Newton minus 5 Newton. Or you can just get rid of the Newton. You don't have to write it because it is assumed that this is forces lah. So 10 positive minus 5. It is on the same axis, therefore I can add them together. No issues. Kalau bukan same axis, you have to resolve. Okay, so this is for this situation. What if your forces are like this? Force 1 and force 2. So we need to declare an x-axis and also a y-axis. In this case, dia dah bagi set-set kat kita. So this is to the right x-axis and this is going upward. This is your y-axis. So if I wanted to resolve my F1, this would be F cosine theta 1. Not theta 2, it's theta 1 sebab ini yang bersentuh dengan F1. F1 cosine theta 1. Okay. This is F1 cosine theta 1. And the axis that does not touch the angle will get the sign. So F1 sine theta 1. So this is you are resolving F1 in this case. Now for F2 kena resolve juga sebab dia tak ada dalam X axis ataupun Y axis, nanti kita nak tambah kemudian susah. So F2 resolve in the Y axis, this becomes F2 sine theta 2. And this becomes F2 cosine theta 2. So if this is in equilibrium, then the net force for this guy is net in the Fx is equal to what is in the x-axis is F1 cosine theta 1 to the right. So that is a positive F1 cosine theta 1. And kita ada F2 cosine theta 2 in the x-axis as well to the right. So yang tu pun dapat positif. So that is your forces in the X. Kita tak cerita lagi pasal equilibrium. Baru cerita pasal equation saja. And then what is your equation for in the Y-axis? The net in the Y, the net of forces in the Y is positive F1 sine theta 1 minus F2 sine theta 2. So that is your equation of your free body diagram. So this is your free body diagram. This is your center of mass. Walaupun tak berapa center kan, but this is the point that they given you. Okay, so that is how you write the equations. So next, what else? So net force, the motion of an object is due to the net force, sum of all forces acting on it. So tadi kita dah solve untuk Fx and Fy. If they ask you, hey, what is the resultant force for these forces? So the resultant force is F net in the Fx squared plus net in the Fy squared, and you square root that. This will give you the magnitude of your force. Kita dah belajar dah pasal ni, magnitude of vector, right? So you need to use Pythagoras theorem in this case, the net Fx squared and plus net Fy squared. And then to find the direction of your resultant force, we use the tangent equation, inverse tangent. So that is net in the Fy over net in the Fx. Okay, sama je. You just need to apply balik untuk forces. So that is your equation. Okay, so now we are talking about parallel components versus perpendicular component. I already introduced this to you guys. In this case, our parallel component is our x-axis. So anything that is parallel to the x-axis will be in the equation. So in this case, your net in the Fx will be minus F plus P. And whatever that is in your perpendicular component ataupun y-axis, net in the Fy is apa ni? Dia tertutup. Sekejap. Reaction, okay. That is your positive R minus weight ataupun mg. This is the equation for this box. The equation for this guy pula, net in the Fx, in this case your x-axis is this way. This is your new x-axis and this is your new y-axis. Kenapa kita pilih sini? Kita selalu nak pilih yang parallel dengan motion, perpendicular dengan motion. That's the easiest one. So your net in the Fx is equal to minus friction plus, what is this? Mana tutup Stress pula. What is here? Oh, tak ada apa-apa. So mesti ada, tak apalah. Kita akan follow gambar ni. So minus F tambah, kita akan ada mg sin theta here. Tak nampak pula. Mg cosine theta here. This is your theta. Okay. So that you would have in your x-axis mg sine theta and Fy is equal to reaction force because he is touching a surface, and also mg cosine theta minus mg cosine theta. This is from his weight. So if you guys notice, bila orang yang main ski, this is what is it called skiing? Okay, tak kisahlah. Benda ni lah kan. Kalau korang perasan orang main ski ni, dia akan guna dia punya weight untuk bergerak. Dia akan guna weight dia untuk bergerak ke depan. Kalau korang perasan dia akan push his body to move. That is because the pushing force ataupun the movement going downwards is from the weight itself. So dia akan use mg sin theta to move forward. So that is the force that is happening here. That is why they need to use the force. And kalau tengok kat sini, dia tengah kecilkan badan dia. Dia nak make sure all the forces are acting towards the center of the mass. And it helps with the motion lah. Tapi ni kita tak belajar lagi. So equation wise, net in the effects is mg sin theta to the right and friction is to the left. So that gets a negative sign. Fy are going upwards and mg cosine theta going downwards. Okay. Okay, so since the motion of an object is due to the net force acting on it, we may rewrite the Newton's law. Apa? Ni kita dah belajar. Ini pun kita dah buat. Okay, so let's do this example. But first, let's take a 5-minute break because saya terlebih masa. Selalunya saya akan break kat sejam. Okay, let's take a break for 5 minutes so that everyone can gather their thoughts and tak rasa penat sangat. So it's 3:26, let's continue. Please get your water or toilet break, whatever. Kalau ada soalan boleh tanya. So no questions for me? Okay. Okay. So our break is over. I hope everyone is back. We are discussing this question. So an object moves on the floor to the right across a frictional surface when 50 Newton is applied to it. So kita ada frictional surface and then kita ada 50 Newton force applied. So kita tak tahu dia, sorry, it's object move to the floor to the right. So the motion is to the right. So if the motion is to the right, therefore the applied force is also to the right. 50. So this is also 50 Newton. And the object encounters 10 Newton of frictional force. So to the left, force is moving to the right. So friction always opposes motion, and F friction is equal to 10 Newton. You don't have to label it here because it's your free body diagram. And then the weight of the object is 80 Newton. So weight is W or mg is 80 Newton or W. Okay, determine the normal force, the net force, and also the coefficient of friction between the floor, and also find the mass. Kejap. Kenapa kita macam skipping points here? So example ni ada kaitan dengan okay, I have to teach you something first before we go to that example. Okay, so for an object is said to be in equilibrium when its velocity is constant. We know this, velocity is constant, which means that acceleration is equal to 0. Okay, I'm going to repeat this. An object is said to be in equilibrium when a velocity is constant or v equals to 0. Boleh juga. So when v equals to 0, it means that it is at rest or it is in static equilibrium. When it is moving, but the velocity is not changing, therefore you would have the change in v equals to 0, which also means a equals to 0. This is known as dynamic equilibrium. And dynamic equilibrium ni korang bergerak. Dynamic ni bermaksud not at rest lah. Dynamic means you are moving, but you are still in equilibrium. You are in equilibrium because acceleration is 0, even though you are moving. So from Newton's first law, the net force acting on the object must be 0. Okay, so kita cerita pasal ni, but this is me introducing this formally to you lah. So we have two types of equilibrium. One is called static. The other is called dynamic. Static is when V equals to 0. Dynamic is when you are moving, but you are still in equilibrium. It means that your velocity is constant. So the F net is equal to 0. So when you have equations yang tadi kita cerita tu, net in the Fx, net in the Fy, this would mean that these guys will also be equal to 0. So now we use this and apply it into our problem. Okay, what is our problem just now? Where is it? What's here? So here we are assuming that in the y-axis, this box is not flying, right? We know that it's moving to the right. And we know that it's still touching the floor. It's not flying. Therefore, there's no acceleration going upwards. There's no acceleration going downwards. We only have gravitational force. Okay, so that means that the net in the Fy is equal to 0. So unless you are flying, unless this box has wings and is trying to fly, then your net in the Fy is 0. So apa-apa benda atas permukaan, dia tak gerak kan? Kalau dia bergerak macam ni, then adalah acceleration in the Y. But when it's just, kenapa tak nampak calculator ni? Okay, when it's just staying there, walaupun dia bergerak walaupun dia bergerak ke kanan ataupun bergerak ke kiri, but it is in the y-axis, kan? Y-axis dia tak bergerak macam ni. Dia hanya bergerak ke kanan ataupun bergerak ke kiri. Therefore, your net in the Fy is equal to 0. So, apa-apa equation yang kita dapat daripada free body diagram akan equal to 0. But kita tak tahu lagi F net in the Fx kita ni 0 ke tak sebab dia cakap it is moving. Kita tak tahu dia moving with constant velocity ataupun moving with acceleration. We don't know yet. Okay, so now let's complete our free body diagram. This is the free body diagram that we have from the information. What is missing here? Anyone? What is missing here?
Normal force.
Normal force, yes. So the normal force is going to be upwards perpendicular to the surface, always 90 degrees. So we have, this is our x-axis and this will be our y-axis. So we know that the condition for our net in the Fy is equal to 0. So I can write my equation, net in the Fy is equal to positive R minus mg, and this would be equal to 0. Sebab tadi kita dah cakap net in the Fy equal to 0. So apa-apa dalam equation ni, R minus mg akan tetap equal to 0 sebab ini kondisi dia untuk dia tak terbang. Kalau dia terbang, yang ni bukan 0 lah, ada ma. So right now it's 0 because it's not flying. So R minus mg equals to 0. This is for net in the Fy. So immediately I know that my R is equal to mg, and we know that mg, or the weight of the object, is 80 Newton. Therefore, my reaction force is 80 Newton. So immediately we solved it using the equilibrium equation ataupun F net equals to 0. So this is our first step. Next, we want to know if this box is going to be moving to the right or if it's going to stay static. Tapi dia cakap move. So we know that it's telling us that the friction is less than the force on the right. So let's try to solve it. So we have net in the Fx equal to 50 Newton minus F. At this point, I don't know if it's equal to 0 or not. So saya biarkan dulu. So I want to know what is my friction. What is the equation for friction in this case? What is the friction punya equation?
Mu R.
Mu R. Do I have the information for friction punya force? Look at this problem. Do we have the force for friction here?
Yes.
Yes,
7
10
Newton.
Newton, right? So F is equal to mu R or 10 Newton. We know what our R is, so mu times 80 is equal to 10 Newton. So now we can solve for mu. So 10 divided by 80. My calculator is dead after that accident. No. And it's a new calculator too. Can anyone help me? 10 divided by 80, 1 over 8 is how much?
0.125.
0.125. So mu is 0.125. What is the unit for coefficient of friction? What is the unit? Okay, saya bagi hint. If reaction force is Newton and friction is Newton, what is the unit for mu? Tengok sini je. Kalau ni Newton, ni pun Newton, mu kena jadi apa? No unit. Tak boleh. Kalau dia Newton, Newton darab Newton kena jadi Newton squared. So it has to have no units. So no unit. Mu does not have any unit. No units. Kena ingat mu does not have any units. Kalau dia ada unit, then whatever that unit is, let's say you say mu is equal to meter, then this would have to be Newton meter, which is wrong. Friction is a force. Force is in Newton. Okay. So F equals to mu R. This is the equation. And from the problem, it says that the object encounters 10 Newton of frictional force. Therefore, your frictional force is equal to 10 Newton. R pula kita dah solve daripada y-axis punya forces. Kita dapat as 80. So 80 times mu should be 10. Therefore, your mu is 0.125. Mu is the coefficient of friction. It does not have units. Okay, so we solve that one. Apa yang kita dah solve setakat ni? So kita dapat coefficient of friction. Kita dapat normal force R. This is mu. We want to know what is the mass. But first of all, kita masukkan dulu friction punya ni. 50 minus F. Sorry, 50 minus 10 will give you 40 Newton. So your net force in the X is 40 Newton. Your net force in the Y is 0 sebab dia tak terbang. It is moving to the right. That's why dia ada force of 40 Newton. Okay, this means that change in V is not equal to 0 lah sebab ada force. When change in V is not equal to 0, you have acceleration. When you have acceleration, you have force. Okay, it goes vice versa lah. If you have force, you have acceleration, you have a change in velocity. Okay, what else? We found out what the net force is. It is 40 newtons to the right or moving to the right. We want to know what is the mass. How do we find the mass? How do we find the mass?
W equals to mg.
Yeah, W equals to mg. So this is C. Okay, let's do number D. So W equals to mg. We know what our W is. This is our 18 Newton. G is 9.81. M, this M, kita nak cari M, equals to 80. So you would get your M as, I don't know, something. 80 divided by 9.81. What is the unit for mass? And what's the answer? Bagi tahu pula. What's the answer for mass?
kg.
8.1.
8.15.
8.15 kg. Okay, so that is your answer. Okay, next. An object of mass 40 kg is sliding down an inclined plane with a uniform velocity. Immediately, we should know what this condition is. Is this in equilibrium or not in equilibrium?
Equilibrium.
It's in equilibrium, right? Change in velocity is equal to 0. Therefore, A equals to 0. Therefore, oops, F net is also equal to 0. Okay, so it is in equilibrium. So draw a diagram to show the forces acting on the object. Let's do this together. Sebab kita nak laju sikit. So this is an incline. Tak tahu angle dia berapa. This is the box. Actually different color. Okay. So draw a diagram to show the forces acting on the object. So we have the typical one, mg or weight. We also have, it says it's sliding down an inclined plane, which means that the motion is to the right. Motion. Ataupun kita akan assume dia ada acceleration lah kot, to the right. So if I wanted to draw the forces, this would be opposing the motion, friction, and you would have reaction that is perpendicular to the surface, and we don't know what is the motion, we don't know what is the force to the right. It didn't provide us. So I need to resolve my mg now because it's not on the axis. My new x-axis would be this way. This is my y, and this would be mg cosine theta, and this would be mg sine theta. Kena tahu benda ni. Okay, so that is complete. Calculate the normal force of the object. Calculate the normal force of the object. First question, is this box flying? Is it flying?
No.
No, it's not flying. Therefore, if it's not flying, the net in the Fy should be equal to
0.
0. It's not flying, okay? So the box is just moving on the slide. It's not flying. Therefore, we know that the net in the Fy over here is equal to 0. And what should be in my equation? You need to help me to write the equation now. Tadi kita dah belajar tulis equation. What should be in my equation?
R, positive R.
minus mg cos theta.
Minus mg cosine theta, betul. Okay, and then so R is basically mg cosine theta lah. Dia tak bagi kita values kan, so kita solve it generically. And then calculate the coefficient of friction. Sekejap. Okay, so it's saying that the box is sliding down with uniform velocity. What should be my net in the Fx? MA or 0?
MA.
What should be my net in the Fx? Condition dia. So tadi kita tahu dia tak terbang. So net in the Fy is equal to 0. This is our condition for y. Kita dapat solve pakai condition tu. What is the condition for net in the Fx? It is sliding with uniform velocity. What does uniform velocity mean?
Equilibrium.
Equilibrium, yes. When you have uniform velocity, it is equal to 0 acceleration, which means that your net forces is equal to 0. Net force in the x is equal to 0. This is your condition for x-axis. Therefore, what should be in my equation for x-axis?
Positive mg sine theta minus F.
Yes, correct. So now we know from this condition, this equation should be equal to 0. So F is equal to mg sine theta. Tapi tak siap lagi soalan ni. Dia cakap calculate the coefficient of friction. Cakap calculate it's asking us to calculate. We only have R and we only have F, and we know that the equation for F is mu R. So let's try to do that. So this is mg sine theta. We don't know what our mu is. Our R is mg cosine theta. So this cancels out. G also cancels out. So mu is sine theta over cosine theta, which is also equal to tangent theta. So here it's saying that mu is a function of theta. Tangent theta is equal to mu. Kalau angle berubah, then coefficient of friction pun berubah. So this is what this equation is saying. So lagi tinggi, lagi senang gelongsor kan? So value dia akan berubah. So bila dia lagi rendah, lagi susah nak gelongsor, coefficient dia akan berubah mengikut angle. So this is what this equation is saying. But you don't have to memorize this one. You just need to know how to do this, to write this equation, how to know the condition. This is the most important part. Okay? Ini just side project dia. Okay, next. Ini dah buat dah. Ada soalan kejap. Does anyone have any questions so far? Doktor boleh ulang balik semula pasal theta tu, yang mg cosine theta dengan mg sin theta. Okay. Boleh. Kejap. Let's go back. Okay, so what did we do for this exercise? So I have an object of mass 40 kilogram that is sliding down an inclined plane with a uniform velocity. So daripada soalan ni, immediately saya dah tahu dah, oh, this guy net in the fx is equal to 0. And it's just saying that it's sliding, right? There's no like terbang ke apa ke. So I also know that the net in the fy is also equal to 0. Just from this question alone, I already know f net is equal to 0. And then I draw the free body diagram. R, friction, box is always tendency to gelongsor, so the motion is to the right. And then we have mg, we need to resolve mg into mg sin theta and mg cosine theta. And then I use the condition from the question and put it for my equation. So net in the fy is equal to 0. What is in the y-axis? Apa yang dalam y-axis adalah R dan juga mg cosine theta. Mg cosine theta ke bawah dapat negatif. And then I equate this to 0 because this is the condition for my forces in the y-axis. Daripada sini saya dapat R equals to mg cosine theta. Saya ada information lain, which is 49.81. I have this value. M saya ada, G saya ada, cosine theta je saya tak ada. That is unknown, right? So R is equal to 40 times 9.81 times cosine theta. The theta is unknown here. And then net in the fx is equal to 0. Macam mana saya tahu? Sebab dia sliding with uniform velocity. So acceleration is equal to 0. Therefore, net in the fx is also equal to 0. So apa yang ada dalam x-axis? We have friction and also we have mg sin theta. Mg sin theta is to the right, it gets the positive. Friction is going the other way, so it gets the negative. So from this equation, we know that friction will be equal to mg sin theta. Okay, kita kat situ dulu . So kalau saya nak letak nombor dia, boleh. Tak ada masalah. Letak je. Sin theta. Boleh. So this is my friction. The theta is unknown. So kat sini, kita pakai equation friction equals to mu r. Let me write it somewhere else. Besarkan group. Sorry kalau siapa yang dah faham and rasa saya slow, I'm doing this for everyone to be on the same page, okay? So hopefully kita semua bekerjasama untuk bagi semua orang faham because we are working as a team. Okay, so just now I told you, okay, so friction punya general equation is mu r, right? This is your equation for friction. This is a general equation. So friction, kita tahu friction is 49.81 sin theta. So let's just write that. 49.81 sin theta. And then mu is unknown. This is what the question is asking. Mu, kita tulis je. And then R is tak nak ni pula. Give me a minute. Sekejap Need to make this smaller juga. Okay. Now I can take this and group it. Make it smaller. Okay. Alright. So saya sambung. So mu is what we're trying to find, and then we know what is our R. Kita dah solve tadi, tapi ada unknown theta. So let's just put it there. 49.81 sine theta. So this is your equation. So kita nak solve for mu. So 40 cancels out with 40, ataupun M cancels out with M. G cancels out with G. Sorry, this is not sine. This is cosine. This is cosine. Right? And kalau korang ingat lagi lah, I don't remember if it's modern maths or additional maths, tangent theta is sine theta over cosine theta. Okay, so when I have sine theta over here and cosine theta over here, if I bring this cosine to the other side, it becomes sine theta over cosine theta. And this looks familiar, so this is actually theta, tangent theta equals to mu. So now my mu is equal to tangent theta. So okay, kita apply balik dekat kita punya incline ni. So what if I have an incline that is 50 degrees, maksudnya tinggi, versus an incline that is condong, 20 degrees, versus incline yang super tinggi, 80. Contoh Okay, kita tengok coefficient of friction dia jadi berapa. So tangent 80, boleh tak tolong kirakan? Saya punya calculator rosak. So tangent 50 and then tangent 20. Berapa coefficient of friction jadi? Can someone give me the answer?
Tangent 80, 5.67.
5.67, okay. 50?
5.19.
5.19.
0.37. 0.36.
0.36. Kenapa dia macam terbalik? Kejap.
Yang 5.19 tu dia 1.19.
1.19. Ya, atas pun sama ke? Yang ni?
Atas 5.
Atas 5.
5.67.
Kenapa dia jadi lagi besar? Sin theta over. Macam terbalik lah. Sekejap. Korang punya calculator in degrees ke radian? Betul ke?
Degrees.
Okay, this is weird. Sekejap. Dan saya nak fikir sekejap. Kenapa mu dia lagi besar? Mu lagi besar. Friction lagi besar ke kalau lagi condong? Okay, I don't know this one. I need to check back on this one. Kenapa dia lagi besar? So basically, what this equation is trying to say that your mu changes with angle. But kenapa dia lagi besar bila lagi condong tu saya tak pasti. Saya kena check balik ni kenapa. Okay, so this one I hutang dulu hutang. Saya kena baca. Okay, so this is what the tangent theta equals to mu means. It means that the coefficient of friction dia lagi besar atau lagi kecil bila kita punya angle ni berubah. Okay, so ada situasi yang macam tu. Alright. Next one. Ini kita dah buat. So, object in equilibrium pun kita dah buat. So now we apply it into exercise. Do we have time? Oh, tinggal lagi minit je. Kita buat example 3.3. Laju-laju Sorry, saya terpaksa lajukan. Tapi tak ada exercise, kita buat terus. So that you guys boleh cover this one. Okay, so it's saying that, korang ada kelas tak lepas ni?
Tak ada.
Tapi takut korang tak faham pula. Tak apalah, kita go like concept dulu Nanti kita sambung balik next class. So a person pushes a 14 kilogram lawn mower. Saya cuba tak lebih masa. So 14 kilogram lawn mower ni mesin rumput lah. At a constant speed. So immediately saya dah tahu dah. Okay, net in the fx is equal to 0. So this is awesome. It's an equilibrium. So senang lah hidup saya. With a force of 88 Newton directed along the handle. So orang ni dia tolak mesin rumput orang putih tu. Kita pakai yang pusing tu. Ini yang dia tolak punya. So this is 88 Newton. This is the force that is pushing the lawn mower. And then we have the 14 kilogram mg. So 14 times 9.81 lah kan, mg. Which is at an angle of 40 degrees to the horizontal. Sorry, this is about the 88 Newton. It is 40 degrees to the horizontal. So masuk kat sini 88 degrees ni dia apply, tapi with respect to the horizontal it is 40 degrees. Kejap, macam mana rupa dia? 40 degrees to the horizontal. To the horizontal. 40 degrees sini. 40 degrees with respect to the horizontal. Does not look right. Sekejap, let me think about it. So macam ni, we apply macam ni, 40 degrees. Okay, macam tu. Saya tak boleh nak bayangkan. So dia sebenarnya dekat bawah. So ni lagi satu benda yang kita kena belajar. 40 degrees over here. So this is 88 Newton. Dia tak cakap below ataupun above the x-axis. It just says with respect to the horizontal. So if it's pushing, it's going to be downwards, right? So kalau dia push daripada atas pun, saya boleh extend my force downward to this side. And with respect to the horizontal is 40 degrees. With respect to the horizontal, it's still 40 degrees. So boleh je ke atas macam ni ataupun ke bawah dia macam ni. Tapi since the force is pushing downwards, it's preferable if you draw it like this. Nanti senang nak resolve. Ada masalah ke kalau lukis macam ni? Tak ada masalah. Tapi nak resolve nanti jadi macam ni, which is not the center of the mass. Boleh je. Sama je jawapan dia. Cuma tak cantik lah free body diagram tu. Susah nak. Your forces need to originate from the center of mass. It will become difficult lah. Okay, so that is why I like to draw it ikut. Kalau dia ke bawah, kat bawah lah. Okay. So, nanti tak apa. This takes practice. Nanti kita akan tengok lagi. So this is 40 degrees. So hari tu saya ada orang komplain, Doktor, fiziks ni semua soalan kibat ke? Ataupun semua soalan higher order thinking skill ke? Jawapannya tak. Tapi example yang kita buat is the higher order thinking skill punya soalan. Because saya expect orang lain untuk tahulah soalan macam what is the definition of a law of inertia? How do you convert meter per second to kilometer per hour? Benda-benda macam tu is not higher order thinking skill. So I expect you to know how to do it. That's why I'm focusing on higher order thinking skill punya soalan. So no, physics bukan deal with semua soalan macam ni. Dalam exam nanti, you have soalan definition. What is the definition of base quantities? What is the definition of derived quantities? What is the unit for luminosity? Benda-benda macam tu is not kibat. It's not higher order thinking skill. And I'm just letting you guys learn it yourself because it's easy. Kita tackle lah benda-benda susah dalam kelas kan. Okay. So continue. Kita tak ada masa. Okay. And then 88 Newton, 40 degrees. With respect to the horizontal, you can write it like this. 40 degrees also. Sama je. Okay. And then mg, and then the lawnmower is obviously on the floor ataupun on the grass. You would have reaction force. and you would have friction lah. Friction. Yes. Because grass is kasar. So tadi saya ada soalan daripada, saya tak ingat siapa dia tanya kenapa semua forces kena letak dekat tengah walaupun so lawnmower ni macam ni kan, dia bersentuh dengan grass kat sini. So friction dekat sini lah kan, tapi kenapa kita letak dekat center of mass? Sebab this is free body diagram, it's not the actual diagram. It's the free body diagram that kumpulkan semua forces at one center of mass. So kalau tengok kat sini handle force kat sini, friction dekat bawah sini sepatutnya, reaction bawah ni juga sebab itu yang dia bersentuh. So reaction kat sini. So dia merata. So kita susah nak jawab soalan ataupun susah nak buat calculation when the forces are spread around. So what we do is, okay, to make things easy, forces should be at the center of the mass so that kita boleh put it into equations x and y. So that is why walaupun friction dekat atas grass, in between the lawnmower, kita still letak dekat center of mass. Because that is the beauty of free body diagram lah. To simplify your objects punya forces. So in this case, it becomes R. This becomes F equals to 88 Newton. With respect to the x-axis, it's 40 degrees. And you have your friction this way. And you have your mg this way. Okay. So that is it for our class. Buat free body diagram dulu. Okay. Take care everyone. Have a great rest of the day. Do not forget your web assign. If you have questions, you can ask me later after class. Bye-bye. Habis dah kelas.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.
Doktor.
Thank you, Doktor.
Thank you, Doktor.
Thank you,
Doktor.
Bye.
Thank you, Doktor.
Welcome. Bye-bye.
Bye.